Good afternoon and good morning to everyone. It's great to be here and hope everyone is having a wonderful day so far. My name is Nancy Andrews and I'm the Chief Engagement and Communications Officer at Canada's Ocean Supercluster, and I'm thrilled to be here with Fabric for this informative webinar. I want to thank everyone who has joined us, and I hope from today's session you gain some knowledge that you can take with you into your work. Because we gather virtually for today's event, we acknowledge the Indigenous peoples of all the lands that we are on today. While we meet in a digital platform, we recognize that our work takes place on traditional territories across Canada. We want to acknowledge the long-standing relationships that Indigenous nations have had with this land, and we are grateful to live, work, and learn on these territories. We encourage each of you to take a moment to reflect on the land you are joining us from and the Indigenous peoples who have cared for it since time immemorial. For those of you who may not know us quite so well, I'll give you a little background on Canada's Ocean Supercluster. We are Canada's national ocean cluster and one of the world's largest blue clusters. Today, we are approaching 1,000 members from across the country, as well as associate members and strategic partners internationally. So really exciting to see lots of growth in this space. Today, we have a project portfolio of about 150 transformative projects, and these are collaborative projects where we often see different sectors and different regions working together. The total value of these projects is about $500 million in total and represents a co-investment with industry and contributes to Canada's leadership, competitiveness, and growth in the ocean economy. Through the work we've done through the Ocean Startup Project, we've helped more than 200 new ocean companies in Canada get a start, accelerated the development of more than 300 new made in Canada ocean products and processes and services to sell to the world, and have built strong global partners in key markets of interest to our ocean companies. And while there is definitely momentum building in this space, and we are excited to see the growth and collaboration behind it, we know there is much to do. That's why we have a bold ambition that has been built together with Canada's broader ocean community. You may or may not have heard of it, but it's called Ambition 2035, where we are collectively have our sights set on a 5 times growth ambition for Canada's ocean economy by 2035, which would put us at about the size of the auto sector. If realized, a recent Conference Board of Canada report tells us that this $220 billion ocean economy could deliver a total economic benefit of $378 billion to Canada, as well as support 1.2 million jobs for Canadians. But to achieve this potential, we need to continue to co-invest with industry and innovation and get more of those solutions to market quickly. We need to attract investment, build capacity, and double down in areas where Canada can lead. In ocean AI, in emerging tech, blue food, defense, security, climate solutions, marine shipping, and energy. And this includes the technologies which we will talk a little bit more about today. Before I introduce our special guest and presenter for today, I want to let you know that we're excited to be participating in an upcoming event hosted by our partner Fabric. This coming event in November, Fabric is hosting called Accelerated, Canada's Semiconductor Symposium 2025, and it's on November 25th and 26th in Vancouver. And for me, it's been a great honor to be a part of the committee that's helping build the conference agenda. And I, in particular, look forward to hosting or moderating what's going to be a really dynamic panel called Harsh Environments and Dual Use, a uniquely Canadian opportunity. And so the panel, no surprise by the title, will focus on the quintessential Canadian subject, which is dealing with harsh environments. With roughly 27% of our land mass above the tree line in Arctic tundra and alpine biomes, massive mineral, energy wealth in remote and difficult to access locations, low temperatures, high winds, and short growing seasons, and oceans which are largely unexplored and not well understood, Canada offers some of the most harsh conditions and environment, but these challenges are a uniquely Canadian opportunity for ideas and technology. It's low volume, high margin business where Canada can lead, where niche semiconductor technology that Canada can produce is a key ingredient, but only the part of the solutions, and the technologies are also suited to contribute to demands of Canada's defense. And this panel will discuss what's needed and where. So if you haven't already registered, I'd certainly encourage you to take a look at the full agenda and consider joining us at the symposium in November, and I look forward to seeing you there. It'll be a great event. Now, we'll turn our attention to today's discussion. It's my pleasure to introduce Luke Govia, Manager, Quantum Technologies at CMC Microsystems. Welcome, Luke.
So yeah, I'm here today to tell you about Fabric and our activities within accelerating quantum readiness in Canada, and hopefully give you a bit more also of an overview of quantum technologies in general and why they might be interesting for you to start paying attention to. Fabric is an ICED-funded SIF, which is trying to take opportunity of the fact that for a variety of geopolitical reasons, the semiconductor industry worldwide, and more generally the advanced technology industry, is at a recalibration point. And we want to make sure that Canada plays a key role in future developments of all these advanced technologies like photonics, MEMS, compound semiconductors, and what I'm going to be talking about today, quantum technologies. To make sure that we really just maximize the opportunity that is presenting itself right now. And Fabric is managed by CMC Microsystems, who I work for, and they're really leveraging the fact that CMC has over 40 years of experience in delivering to the Canadian ecosystem things like the infrastructure required for computer-aided design tools and other advanced technology development tools, working with global fabrication services to enable hardware prototyping and design. Beyond just being able to deliver these technologies and these capabilities to Canadians, we also have an internal team of engineers, scientists, and technologists in general, all of whom are really have deep technical expertise in these advanced technology areas, so that they can assist the Canadian ecosystem in its development and research. And we work both, globally as well as within the country. So Fabric itself has a few different approaches to making sure that Canada's semiconductor ecosystem is being accelerated. And generally, these approaches leverage funding supplied by ICED through a few different pathways. The first being our challenge funding, which is the predominant source of where we are able to support Canadian entities. There's two different tracks for that, and these are really sort of, I'll talk about more in detail about that shortly, but they're large-scale R&D efforts that Fabric supports. We also offer low-cost access to design and fabrication tools, to both the CAD tools as well as access to fabrication facilities globally. Another very important aspect of what we do is training. And we're really looking to do training of highly qualified personnel so that they can move across industry or into new industries as the market demands. It's a 5-year program, and it's open to industry generally in Canada, SMEs, startups, and large firms, open to not-for-profits, open to government agencies, and also on all post-secondary institutions like universities or colleges and whatnot. A bit more about the challenges, since this is the bulk focus of Fabric. It's like I mentioned, it's broken into two major buckets. The first being on fabrication process development, which is really making sure that we in Canada have a secure supply chain for developing and building in country these advanced technologies, whether they be MEMS, photonics, quantum, or semiconductors, or playing an important part in the global supply chain for these technologies. On the other side is more focused on commercialization of devices and products. So in particular, IoT and edge devices, things like new sensors or edge compute devices. And generally, the challenges support up to 40% of the R&D costs associated for small and medium-sized Canadian companies and academics for building either bringing these products to market or securing the supply chain. So we recently finished the first round of challenge calls, and the first round of awardees announced. It's 20 companies overall, or 20 institutions, I should say. And within quantum technologies, there were 4 of them, 3 in the fabrication process from Eponix, Anion, and CTOMI, and then Quantum Recon, and then 1 in the product development from Cubic. And I just want to flash an advertisement that round 2 is actually launching very soon, early this month. So, if you want any further information, or if you're interested in learning more about the product challenges, please see this website, or of course, reach out to me or ask questions. So, the focus of today's talk is quantum technologies. So I want to be a little bit more concrete as to what Fabric does in that area. And really, there's sort of two main focuses of the quantum technologies team within Fabric. The first is helping take quantum technologies to market. So that's both at the early stage R&D so that there is a capability that needs to be commercialized, ending in the commercialization efforts, and in the middle, working to make sure that there's an end sector adopter for the technology. So this is sort of the context of talking with you all today. The other aspect is to help bring Canadian companies not within the traditional realm of quantum technology, both companies and researchers from academia, into the sphere of quantum information science, whether it be adopting quantum computing solutions to their business problems, right? Or actually starting to develop quantum products themselves that may be useful for their end sector applications. That's, the other focus of today's discussion. All of this is within what we call the innovation platform for Fabric, which is separate to the challenge platform, where the focus is on training to upskill HQP, bring people with quantum ready skills into the workforce, and also higher level training to help, to help people who are not quantum native understand what the benefits and value is in quantum technologies. Also on quantum application development, here we work with end sector clients to bring quantum computing solutions in particular to their business cases. And finally, continuing the long-standing tradition that CMC has in device design and fabrication prototyping, we have a pillar of our work in the innovation platform for quantum is in device design and prototyping, in particular for quantum devices. This is actually only available to Canadian academics. Just always want to make sure that's clear. But we deliver state-of-the-art CAD tools as well as cost sharing for fabrication. So that's a kind of an overview of what Fabric is and at a very broad strokes, the things we do. And I will at the end talk in much more detail about what in particular CMC's quantum technologies team can do for you if you're interested in stepping into quantum technologies, or if you already have and are somewhere along the journey. But I think first, I wanted to maybe set the scene a little bit and answer the question of why now? Why is it now that Canada and the world is becoming very interested in quantum technologies? And before I answer why, I thought I would make it clear that this is happening. And I think one way is to center around Canada's National Quantum Strategy, which came out recently. And this is really a document that's meant to focus Canadian investment and development towards achieving Canada as a key player in quantum technologies globally. And it has three key missions, and this is a lot of words to say three very simple things, those 3 bullet points. The first is to ensure that Canada is a major player in quantum computing. The second is to ensure that our security systems are robust against the potential of quantum computing-enabled attacks. And this boils down to deploying post-quantum cryptography, both at the government and private sector level within the next 10 years. And then the last bullet point is to ensure that we are both developing and adopting any new quantum sensing technologies that come out as they're being developed. So that's the 3 missions, and the pillars of that, how Canada is going to achieve that, is of course through supporting basic science research and helping it move to applied research and eventually commercialization. That's the first 2, or the first and last pillar, and then the middle one, of course, is to continue that we have is to ensure that we have a strong talent pipeline, and that doesn't mean just training, because Canada has a long history in doing some of the best training and having some of the most world-class training institutions in quantum computing and quantum technologies in general, but also retaining that talent. And that has been historically the struggle that Canada has faced. But that's our strategy. And to put some concrete numbers on it, we can compare Canada, the government of Canada's investment in quantum technologies, or promised investment, compared to global investment. And you can see sort of where we fall. So the government of Canada has promised to invest $360 million in Canadian in quantum technologies. And you can compare that to our much bigger neighbor down south, who, with a factor of 10 population, has promised to invest a factor of 10 more over the next 5 years. But even if you compare to similarly sized economies and countries like Australia and Netherlands, there have significant more investment in quantum technologies. Of course, everyone is outpaced by China, but it's a little bit hard to know whether or not that number is accurate. But it really shows that there's definitely gap and room for the Canadian economy and the Canadian ecosystem to pick up, whether it be from private sector investment or otherwise. But we are lagging behind the world. But the now question, I think, is best answered by this chart. So what this chart is showing is total investment with some caveats, but public and private money into quantum technology companies over the space of the last 12 years. And you can see that there was a tremendous inflection point around between 2020 and 2021, where it went from hundreds of millions of dollars in investment per year or less to billions of dollars US in investment. And this has really been driven by what's happened in the last 5 years, especially in the quantum computing space in terms of demonstrations of early progress towards solving useful problems. So this chart is broken up in terms of the stage of the investment. It gives you a sense of where along the timeline some of these companies are. But I thought it was also interesting to look in terms of what countries are investing. Now this chart, is capturing sort of investment into private companies, which is why the Chinese parts of this chart look so small, because most of their investment is in publicly held institutions. But you can see, of course, in investment into private entities, the US dominates by far. And Canada actually is one of the top investors here, at least in proportion, if not in overall dollar value. So, the natural question then is, why is there now all of this money in this technology space? And the answer is because of what we call the second quantum revolution. So you are all, at the very least, familiar with what happened because of the first quantum revolution, whether or not you are aware that it happened. But in the 1990s, when quantum mechanics was developed by the likes of Bohr and Einstein and Heisenberg and Schrodinger, that really allowed us to explain the natural world and develop physical theories with accuracy that was unprecedented. And just some of the many things that have happened as a result of this include the development of semiconductors and the transistor, so wall of computing, lasers, and there's many other, of course, things that have come out of this. It's really been the hallmark of material science and quantum chemistry over the last 100 years, right? And the world we see around us is really because of the first quantum revolution. And nowadays, we say we're in the midst of the second quantum revolution. And what distinguishes that from the first is that the second quantum revolution is really about harnessing entanglement and superposition, so fundamental properties of quantum systems, to enable enhanced information processing. And that sort of manifests in three major ways. The first is what we call quantum computing, right? Where we're using entanglement and superposition to perform computational tasks. And that really has the promise of exponentially faster computation on a select set of problems. And I really want to emphasize the select set there, right? The second quantum revolution is said to have started roughly in 1994 when Shor published Shor's algorithm, which is the most famous of these exponentially faster algorithms because it breaks the commonly used RSA encryption algorithms and a few other encryption algorithms that we use. And that's sort of really the genesis of when the second quantum revolution began. The other way that this manifests is in quantum sensing, which is using, again, entanglement and superposition to improve sensing in a way that can give you polynomial improvement in sensitivity. And I want to, again, make that very clear. I did not use the word exponential here, right? Quantum sensing only promises polynomial improvement, but of course, when it comes to sensitivity or resource allocation for a quantum sensor, that could be tremendously impactful in a practical sense. And then finally, the other big bucket of the second quantum revolution is quantum communication, right? And that promises provably secure encryption. So that means that encrypted message sending, through which by the laws of physics cannot be broken, right? Of course, everything has loopholes, everything has attacks, but this, as far as we understand the way information processing works in the universe, you cannot break this encryption efficiently, I should say. But I think another knock-on effect from the second quantum revolution that we're really seeing, especially as to why there's so much business value being driven now, actually has nothing to do with entanglement and superposition, and it has nothing to do with what purists like myself would call pure quantum technologies. It's actually the fact that in trying to build quantum computers and in trying to build quantum sensors, there's been a tremendous amount of technology development in those core underlying technologies that underlie quantum information processing, but can also be used for other things. And they've led to better development of, for instance, better classical sensors, right? So things like magnetic field sensing with diamond envy centers. There's no quantum enhancement here, but because we've made much higher quality diamond envy chip sensors or diamond envies, we can do much better magnetic field sensing with them. Another kind of neat one, although this is a bit more on the theoretical side, is something that's called super resolution, which is the ability to distinguish point sources of light beyond the diffraction limit set by the wavelength of the light. So it was actually not known how to do that, what the optimal limit for this was, and it was proven what the optimal limit was using techniques of surrounding quantum information processing. But in doing so, it was actually discovered that the optimal procedures are not themselves quantum. It can be done classically, but those were not we were not able to discover those with classical means. So I want to emphasize, I think a lot of the near-term value that we're seeing from the second quantum revolution has no information processing at all beyond what can be done classically, but it's just the development of better technology that has usages both for quantum information processing and for other applications. So we can start, I'm going to talk now a little bit about some of these applications. And the first one I thought I'd mention, which is, probably near and dear to this audience's heart, or at least has the strongest connection, is an application in the marine ecosystem. I noticed recently that a quantum computing company called Entanglement recently acquired Applied Ocean Sciences with the goal of improving their research through quantum-inspired algorithms for things like marine conservation, environmental sustainability, and monitoring coastal risk analysis and ocean acoustics. So an important point to make here, and this is the reason I started with this one actually, is that this is not a quantum algorithm, it's a quantum inspired algorithm, which means that again, you're going to get no exponential speed up, right? It's a classical algorithm that's going to give some heuristic polynomial improvement over existing approaches, but it has been developed from insights gained from trying to develop quantum algorithms, right? So there's been a lot of work actually across a variety of domains where in trying to build quantum algorithms for specific problems, people have come up with better classical algorithms for it. And this is one example of that. There's again another one of these knock-on effects of all the investment in quantum technologies. But if we go to more, actual advantageous quantum algorithms, we can look at things like quantum chemistry on a quantum computer. Recently, IBM and their colleagues at Riken have put out some great work, and this is just one example. Actually, there's been several follow-ons since then, doing quantum chemistry beyond what a classical supercomputer can do exactly. Right, and this actually leverages both the quantum computer and the classical supercomputer together to work harmoniously to solve this problem. Another example similar is material science studies on quantum computers. For instance, Google here has demonstrated studying time crystalline order. This is a many-body physics problem. And generally, there's a lot of hope that discovery science, while most of these algorithms are heuristic in the sense that we can't prove what kind of speedups they will have, they seem the most natural candidate to get exponential or strong or very fast speedups compared to what can be done in classical computers, because we're using a quantum computer to simulate quantum physics, right? Whether it be quantum chemistry or material science, these are all natively quantum problems. So this is always considered a very promising aspect and one that has, a lot of potential application in drug design or biology or studying reactions within wet environments. All of which, are very interesting for scientists and for business use cases as well. The other big area where there's believed that there will be some quantum advantage from quantum computing itself is in optimization. So recently, D-Wave, who are based in Vancouver, announced that they have a new hybrid quantum classical application for optimization applied to autonomous agricultural vehicles. And generally, people have looked at optimization problems for many different domains, whether it be vehicle routing like this one, or manufacture, power management even as well, and finance is a very big and actively studied area. And all of these sort of give basically, again, heuristic solutions in the sense that for in most cases, we cannot prove how much faster quantum algorithms can be, but there are actually some specific cases where we can show that there are exponential or strongly polynomial separations. And this all points again to the benefit of using a quantum computer to solve these problems one day versus a classical computer. So in communications, I want to point out actually that, it's been almost 20 years that people have been using quantum communication in the world in practice. And in particular, the Swiss federal elections have been using quantum cryptography to secure their data for quite a long time, actually, since 2007. But perhaps one of the more exciting applications of quantum communications is actually pushing it into space to enable long range communication. And China has done this, beaming information from China into South Africa with a satellite relay in between. Boeing is investing very heavily on this technology internally as well. And there's a large-scale Canadian project funded by the CSA and the University of and managed by the University of Waterloo to launch a purpose-built satellite for quantum key distribution, which is the precursor to secure communications enabled by quantum technologies. And that's supposed to launch in 2026. And they've actually already demonstrated an airborne version of this, not yet in space, but at least in the sky. And then finally, in that last bucket of quantum sensing, I want to again reiterate the point I made earlier that a lot of the near-term benefits we're going to see from quantum, from quote unquote, or from quantum technologies in the sensing domain are going to be improvements to classical sensing techniques that come from better hardware. Right. And really, the underlying reasons for this is that the technologies that make good quantum computers are very good sensors as a result, because they're very well isolated from anything but the signal you want to measure. And yeah, these benefits can really be used now because they're not coming about as a result of entanglement or superposition. So they don't need to wait for the full revolution to finish. There's some very interesting quantum or Canadian startups in this space. For instance, SP Quantum, who have developed this diamond envy center magnetometer that I mentioned earlier, and they're using that for mineral exploration as well as to map Earth's magnetic field. And then you have Phantom Photonics, who are a LiDAR company for underwater imaging, communications, and spectroscopy, who are again using advanced technologies coming out from developments for quantum communications. So that's a very high-level overview of quantum technologies and what they're useful for. And there's many things I left out. I could spend hours and hours going over all the potential applications. But I want to move on now to talk a little bit about what we can do for you if you're interested in quantum technologies or if you're already along the journey. And the first, of course, is like I mentioned, is training. Right. We host every year several virtual workshops on software training to help people learn how to program a quantum computer and how to run quantum programs on real hardware. We do this often in collaboration with externals, particular people who build and host quantum computers like Pascal for neutral atoms or offshoots of IBM for Qiskit and for their hardware approach. We also have a higher level training that we used to call Quantum Technologies for Non-Techies, and now we call Quantum for Decision Makers. That's really aimed for people who are just beginning their journey in quantum technologies and want to understand what the capabilities and potential are for their business. We also do a lot of training for quantum hardware. I like to advertise that in a couple of weeks, we're going to be hosting a Build Your Own Superconducting Quantum Device workshop at the University of Waterloo and the Institute for Quantum Computing. And this is something that we've hosted several years now. And it really gives people a firsthand experience with how to design, simulate, and ultimately test devices, superconducting devices that are used for quantum information processing. We do a similar thing for quantum photonics for silicon devices in particular. Beyond training, the next sort of pillars that I want to focus on that we can offer is hardware prototyping. So like I mentioned, we have a fleet of CAD design tools that we can give access to, particularly to academics, to enable design and testing for quantum devices. And we also have agreements with many of the fabrication facilities globally and within Canada to enable low-cost fabrication runs for these devices. So we can help, from the design and the rule checking to make sure that the design will fabricate all the way down to actually enabling the fabrication itself. And in particular, I'll call out the superconducting device one that we have that we're bringing up with 3IT in Sherbrooke. And then for end-sector users like yourself, I think maybe the easiest or one of the main entry points is in quantum computing, right? And trying to develop applications and algorithms for your use cases, your end-sector business use cases for quantum computers and finding quantum solutions. So we can enable access to some quantum hardware through our partners, indirect access to the cloud, ones like IBM Quantum through Pink. And we will really work in close collaboration with you to make sure that, not only is the algorithm being developed properly for the application, but you're getting the most out of the hardware to make sure that it runs performantly. And I want to mention that within the next month or two, we'll be launching our Quantum Sandbox program, which is a Fabric-funded initiative to give direct access to quantum computing services to Canadian SMEs and academics. And not only will this program fund the access, it will also fund my team's time to support the access, both from technical aspect as well as sort of co-developed engineering R&D to make sure that you're to bring your business use case to quantum technology or to quantum computing. So a little bit more detail about how we approach this, right? This is really a multi-phase process, starting from the ideation and road mapping of what is the use cases and what are the benefits, the potential benefits of quantum computing for your particular problem. Moving to a proof of concept where we help develop the algorithm and see if it's going to work on available quantum computers. And then finally, understanding a demonstration of it potentially on real hardware, and then seeing what will happen in the future. How will it scale? What's the potential for long-term business advantage? So we've done this for about 35 different projects since in the last 5 years across a very wide range of application domains, as you can see here. And we've worked with a lot of different partners across Canada, both universities as well as small enterprise. So that's it for me. I did want to again flash the advertisement for Accelerated, our semiconductor symposium that's starting that'll be in November in Vancouver. And associated with that is also Texpo, which is a graduate student research competition which offers cash awards across all of CMC's technology domains for outstanding Canadian innovation and research. So if you have any questions about that, ask me, or please take a look at these links here. So I'll just end by saying it was my pleasure speaking to you all. This is the quantum team at CMC, and I am really happy to help you a lot wherever you are. And if you want any more information, please reach out to me, and I'm looking forward to hearing your questions. Thank you.
So much, Luke. I think I successfully made it back on. That was a great presentation. I think lots to take away there. So I do want to give folks an opportunity, a couple minutes to put any questions you may have in the chat, or not in the chat function, in the Q&A button. So you'll see that at the bottom of your screen. We'll keep an eye there. So take some time now if you have any questions. I do have a couple here though, Luke, for you in the meantime, just from a broader, I guess, a big picture perspective. What do you think Canada can really do to best leverage its expertise, both from an ocean perspective, but also from a quantum perspective, to really build global leadership in this space? Kind of a big question, but.
Yes. So I think for me, the biggest thing that Canada can do is to leverage the fact that we have always been world-leading researchers in those two areas. All right, both in quantum computing, where a lot of the foundational work was done in Canada, as well as in oceans, where we naturally have many reasons to be experts in oceans, right? And I think what we're missing now is the interconnection, right? Bringing all the important stakeholders together, and bringing, more importantly, people who are willing to do the work to put together the pieces for a larger picture goal. Right. I feel like there's too much siloed research right now, too much siloed development, and being willing to take the risk, of exposing yourself to direct competition, right? To open yourself up to working together to achieve something that you couldn't achieve individually.
I'd say too that is likely a role that Fabric and the Ocean Supercluster, both as funders and conveners of networks, can probably help bridge the gap there a little bit. I'm just going to jump to the Q&A. So someone's asking, can I sign up to Fabric as an individual independently from my company, or do I need to get the organization registered?
You can sign up independently, I believe, although I think it's generally beneficial although the Fabric structure is typically best suited for, I think, organizations to register rather than individuals rather than repeating many people from one organization registering.
Okay, so hopefully that answers your question. I think it was
Yeah,
Will.
sorry, I don't have a lot if that wasn't a good answer.
No, that's great. So we can make sure folks get, we'll make sure people get the, so Will says thank you. Okay, great. So folks, put any more questions you have in the chat. I do have another question around, so I mentioned that the OSC and Fabric, I think, probably have a role to play there in the work that they're doing. And so I just, there's lots to do in this space. And so is it fair to ask, like, what's the biggest roadblock you'd consider to using quantum in the ocean industry?
Yeah. So I think, well, I think the biggest roadblock is actually knowing what to use it for. So I think, there's a tremendous amount of, I should be clear, right? Like quantum computing in particular and true quantum sensors and all of these, like really leveraging quantum properties for enhanced information processing. There are tremendous technological roadblocks before we get there. Right, but those are well addressed by the quantum computing and quantum technology community, or being addressed, I should say. Right, I think what's lacking generically from end sector users, in particular, and like the Ocean Supercluster and the companies, is what are the problems that are really important. And I think there's been a lot of sort of people from quantum computing trying to find problems that might be useful, or people from end sector users seeing some quantum solutions and trying to apply them to the obvious problems. But I think where we're going to see really transformative potential is when there's more dialogue between those two, so that the core issues, the core problems that underlie things can be identified and and potential solutions can be developed.
So that makes a lot of sense. And it's more about, I understand there's a collaborative opportunity there that maybe we're not fully leveraging yet. Our sector is made up of a lot of small, medium enterprises. And so just wondering, how can smaller companies prepare for quantum without big R&D budgets? Like, what's their approach there?
Yeah, I mean, I think that's challenging, and I think if you look at the investors right now, right, it's predominantly really large firms, Bank of BMO, for instance, in Canada, or you look at Boeing, HSBC, these large who have deep pockets, right, and can have some internal R&D. I think if that's if that's outside the reach of a smaller firm, which of course it is, right? The best thing there is to try to work with trusted partners, right? Who can keep you abreast of what's happening and understand when there might be developments that are useful. And I think I'll selfishly, shamelessly plug CMC. That's a role that we're really trying to play both within and outside the scope of the Fabric program. As a not-for-profit in Canada, we don't really have any skin in the game, right? As to why we want to push our algorithm or our application or our hardware, right? And we're really hoping to work with interested parties to make sure that they're ready for quantum technologies when they are deployed, or when they're playing an active role in shaping what deployment even means for them.
I won't name the person here, but I'm just wondering, Luke, we have someone who said that they have a list of ideas they hope this tech can help with, and they're looking to understand, would there be an opportunity to connect with you or someone to shortlist their ideas, validate who might be good partners, just what's the right way to navigate. So I guess my question is would we be able to circulate kind of a contact for folks if they want to reach out and have a discussion around these sorts of things following the
Absolutely.
webinar?
Okay. Yeah,
Okay.
absolutely. Please, feel free to contact me by email. I think you share my email to everyone that was registered. I'm happy to have those conversations. That's well within what we're trying to do here.
Yeah. So we'll make sure everybody has that following today's webinar for sure. Okay. And so I guess for me, and I don't know if you'll love this, but what is the one thing? So we're looking ahead. We've talked about, some of the barriers. We've talked about, how SMEs approach this, the roles of organizations like Fabric and the Ocean Supercluster. For the ocean sector, for ocean sector businesses, what's something that they can be doing today to get ready for, for a quantum future? Like what are the things that they need to be thinking about if they're not already or doing?
I think the things what I would do is I would look at your technology stack, right? And I would say, okay, what are my bottlenecks? And what are the things where there's no clear path to solution, right? What are the key, for instance, like I'm just gonna ballpark an example here, right? Like imagine, or ballpark two examples. Imagine you're maybe a company who's interested in chemical reactions in the ocean, maybe some biological driven things, for instance, right? Ocean acidification or something, right? And you're stimulating this technique, this to try to understand how this plays out in real world conditions, right? So you might have some software simulation stack for doing this. You could say, okay, what are the slowest pieces of that stack, right? And what's the both academic as well as industrial R&D around making that faster, right? And if the answer is, okay, there really isn't any, or things that sort of seem like they've hit a roadblock, that's the kind of area where, not knowing anything about the problem, where we might say, okay, let's see if quantum computing, which is a new paradigm for computation, can work here, right? Now, the answer might be no, right? But it's at least, but if you have limited opportunities otherwise to begin with, it could be worth a shot, right? And then another example, say you're doing marine monitoring, for instance, right? And I'm really stretching my understanding of ocean technologies here, but let's imagine you're doing this, right? And you have a sensor, right, that's collecting data. Again, I think you asked the question of, realistically, how much can I improve the sensitivity? How much can I reduce the swap constraints for the sensor using the technologies that exist, and where we see those technologies going in the next 10 years, which, obviously you're going to be an expert for because this is your bread and butter, right? And if the answer is, it's a lot of money and it's a lot of slow R&D, right? Then maybe there's a potential there for quantum sensing as well, or one of these other technology domains that are a knockoff from quantum technologies that are still doing classical sensing, but with some sort of advanced technology. And there I will say, like, for me personally, if you ask what am I most excited about, it's actually the concept of merging quantum sensing, or at least quantum inspired sensing. So the sensing of classical sensing, but with co-compute. So co-located computation on the edge. And of course, I think a lot of people are excited about that in general, but I will say that quantum computing has a big place to play in that as well, because of its ability to process quantum data locally.
That's awesome. And so I think we've addressed the questions in the chat, and lots to take away from today's discussion and to consider. And I think there are things that we all need to be thinking about and doing in light of today's discussion.
Yep.
And so I just want to say a big thanks, Luke, to you, and of course to our attendees for the valuable insights and discussion today.